Today we are going to talk about hidden surface elimination, right. So, the motivation is that, as we have seen in the case of clipping, right, what does clipping offer? It actually eliminates the portion of the scene which is not contained in the viewing frustum, right, in 3D. So, similarly, there are issues like when you want to display the scene, right, there are portions of the object, or there are objects which are hidden by other objects, right, and you would not like to display them, right. So, eliminating what is hidden is what we study under hidden surface elimination. Okay. So, that basically requires you to determine the visibility of the objects or part of the objects which should be displayed, right. So, sometimes it is referred as visibility detection or visibility determination, right. So, just to sort of motivate you as to why this is pertinent. So, let us say if we are considering an option of displaying a 3D object in its wireframe form, that means I basically display the edges of the polygon using lines, right. So, this is what I have in the wireframe. So, clearly it is not known whether the object is this or the object is this, unless I perform the hidden line elimination. That means, the lines which are hidden are not displayed, right. So, if this is the situation, then I know that this is actually in front, right. This line and the face corresponding to this line is in front, right. So, I get this. Similarly, if this is the situation, then I know that this face or the lines corresponding to this face are in front, right. So, this way of removing the ambiguity is obtained through hidden line or surface elimination, right. So, we are going to look at the various methods and ways by which we perform this, right. One of the methods we have already seen, ray tracing, right. Ray tracing does it, by its inherent nature of rendering, right. So, you shoot a ray and then you find out the intersection, and the closest intersection point is the point you render, and that already takes into account for the visibility, because that is the frontmost point, right. So, you have already done some of the hidden surface elimination. Okay. So, if you look at, let us say, another example here. So, here you have this wireframe scene, right. So, these are the various lines which are displayed, and so one can look at the problem in terms of, as I said, hidden line elimination, where you are plotting or displaying the lines, right. This was of particular importance when in the earlier days these plots were drawn on the screens of 3D objects, right. Only the line drawings were done, right. Or you may be actually referring to the hidden surface elimination, where you are looking at the face or the polygon or the surface for which you determine the visibility, right. So, one may be solving hidden line elimination or hidden surface elimination. So, in today's graphics we generally do hidden surface elimination, right. We will look into at least one of the methods which refers to hidden line elimination, but majorly we will talk about hidden surface elimination, right. So, when we talk about the approaches for hidden surface elimination, and in fact, one can see it in two ways. So, there could be two ways to look at the problem, depending on how you are performing the computation or where you are performing the computation. Right. So, one could be what we call it as image base or image space method, right. So, here what we are doing is we are basically determining the visibility per pixel. So, it is a through pixel, right. For a given pixel you want to determine what is visible in the scene, right. So, that is a image space approach. The other approach is object space approach, where you try to see among the objects in the scene or the parts of the object for the object itself, what is the portion or the objects which are visible or which are occluding other objects, right. So, the computation which you are performing is in object space, right. So, just to further elaborate on the two methods. So, in image space approach, what we are doing is, for each pixel in the image, we determine the object closest to the viewer, right, that is intercepted by the projector which is coming from the center of projection or the eye, right, through the pixel, right, and then we draw the pixel in the appropriate color. Right. So, that is what happens in image space approach, right. So, the precision of the computation is the pixel, right. So, if you want to look at the computational effort which is given here is, if I have, let us say, n as the number of objects in the scene, p as the number of pixels on the screen which need to be rendered, right, then the computational effort is of the order n times p, right. For each pixel I am basically determining out of the n objects which part of the object or which portion of the object or which point of the object needs to be rendered, right. So, that is the order of computational effort. On the other hand, if we are talking about object space approach, right. So, here we are looking at, for each object in the world, determine those parts of the object whose view is unobstructed by other parts of it or any other object, right. And then you draw those parts in the appropriate color, right. So, the precision in which you will be working will be the precision with which you define the object, right. That is the difference. And if you look at the computational effort, since we are talking about n to be the number of objects, so it is going to be of order n square, because for every object you are going to see what happens with respect to the other object, right. So, that is sort of an overview of the two approaches, the image space approach and the object space approach. Right. So, now let us see some of the methods of these hidden surface elimination. So, one of the method which is more from the historical perspective and which is actually speaking is hidden line elimination is this floating horizon algorithm. Okay. So, typically we are looking at a surface which is defined in a functional form like f x y z equals to 0, right, and one can do the plot of this function considering the slices at different z, right. So, for instance, for one particular value of one constant value of z, I can make a plot of this, right. Therefore, find out x and y. Right. So, x is another, let us say, function g y z, and similarly y is another function some h x z, right, just to have a 2D plot. So, if I do this, basically the function may look like this, right, and all these values z1, z2, z3, z4, z5 are these constant z values where the section of the surface is considered, right, and these are the corresponding plots of the surface for a particular value of z. Right. So, now what we are trying to do is figure out what portion in that function should be visible, right, and there is an implicit order by which we are looking at this is from front to back. That means, the front is frontmost z is z1, then z2 and so on, right. So, if I am doing a plot in the order of front to back, then how should I make sure that the hidden line or hidden curves with respect to these plots are not plotted, not displayed, all right. So, in order to do this, so what do we have with z is equal to constant, which is a plane closest to the viewpoint, that is what I meant by front to back order. The curve in each plane is generated, right. That means, for each x coordinate in image space, the appropriate y value is found. That is what I mean, right, by generation. And let us say we are looking at the projection on z is equal to 0 plane, right. So, that is what you will find out, that is what your generation of curves is going to be z1, z for z1, z2, z3, z4 and z5, right. So, when you look at this, one can propose an algorithm, right. So, what is happening is, if you look at the plot here, right, at this point for z is equal to 4, this is the portion which is actually hidden, right, this part, this particular part, right. So, one can propose an algorithm where one says that if at any given value of x, the y value of the curve in the current plane, right. So, z3 is already plotted, let us say it is a previously plotted plane, and now we are plotting the curve for z4, right, going from front to back. So, then we are saying that value of the curve in the current plane is larger than the y value, right, for any previous curve at that x, right, then the curve is visible. Fine. Otherwise, it is hidden. So, for this part of the curve, it will turn out to be hidden, right. So, it is a very simple way of thinking, very simple algorithm, right. Now, the question is, does it work always? Does it work? What happens if instead of having this, and peak there is a sort of a valley, right? Then you are in trouble. It doesn't work. But actually, it requires a very small modification even to account for that, right? So, what are we saying? We are saying that, so this is the scenario here, right. So, you had a plot here for Z1, plot here for Z2, and this is the plot for Z3, where you observe that it actually dips down, right. And according to the algorithm which we had just looked at, these would not have been plotted, these would have been declared as hidden. Right. So, what do? You modify this and say that if at any given value of x, the y value of the curve in the current plane is larger than the y value, this is what it was earlier, or smaller than the minimum y value, right, for any previous curve at that x value, then the curve is visible, right. So, you also need to look at whether it is smaller than the minimum y value for that x. Fine. So, in this situation, if this point is to be considered, then you would find this is smaller than the minimum y value, and therefore, you would display it, right. Then the curve is visible, and therefore, you display it. So, in a sense, what we are looking at is some sort of a horizon, right, which is defined for the y values, which you keep shifting, right. This minimum y value is nothing, some sort of a horizon which keeps floating, and then you always compare to that horizon, right. So, that is why it is also called as floating horizon. Fine. Of course, there are other smaller issues which are also concerning, because much of it depends on the sampling of your screen, right. Anytime you want to display a point, then you will need to sample the screen, and then you will figure out whether this point lies there or not, right. And then you may actually require to do an interpolation, right. So, these are not continuous things, these are actually discrete points when they come to the image, right. But at a gross level, this is what the algorithm is. right. So, here we are basically dealing with hidden line elimination, because we are just plotting the lines or the curves. Okay. So, now we look at another hidden surface elimination, which also you have seen in some other context, is what we call it as back face culling, right. So, what is back face culling? Back face culling is something which helps you declaring that this polygon or the face in an object is facing backwards, right, and therefore, you need not display it, right. So, to determine whether a particular face is a back face or not, it's a simple test which you look at with respect to the normal of the face you have, say point P, this is the face you have, and this is your viewer here. So, V defines the direction from the face to the viewer, right. Then all you are talking of taking a dot product of this normal with respect to the vector V and check the sign of it, right. So, if it is less than 0, that means it is negative, then we are saying that the surface normal is actually pointing away from the viewer, right, or it is facing backwards, and therefore, do not display. Right. So, it is a very simple way of eliminating the back faces. Fine. So, this is as it says, is actually a pre-processing step. This does not take away all the faces which are possibly not visible, right. It is actually a conservative kind of an algorithm, right, in the sense that let us say if I have these faces, right. So, I have plotted them in 2D considering z and x section, right, and all these arrows are basically showing the normals on those faces. Okay. And let us say the viewing direction is somewhere there. So, I am looking at in this direction, right, from here to here. Fine. So, what will happen using the back face culling method? Some of the faces will be marked as back faces and therefore, should not be displayed, right. So, these green ones are basically the back faces, right. But if you look at this is a face which is still not visible, right, because it is actually obstructed by this. So, it does not consider that. So, that is why I meant by the algorithm is conservative, right. So, it is a pre-processing step you may require to flag out the faces which should not be displayed, and then maybe you need another pass of some other hidden surface algorithm, right. So, similarly, it is actually only partially visible. So, those things are not determined by this. It just declares whether a particular face is a back face or not, and that is all, right. but it is a very simple and straightforward way. Right. Okay. So, now the next technique, which is very popular, is the Z buffer algorithm. Have you heard about this name? Since you have been using OpenGL, you might be declaring it somewhere. Depth testing, Z buffer, right? So, it was actually proposed by Catmull back in 1974. It's a very old method, but it's still used, extremely popular. It's very simple to implement, right? So, what happens here is that you consider a Z buffer, which is something like a frame buffer, right, which maintains the depth of the current polygon or the primitive which is being drawn, right, in that buffer. So, it basically contains the information of depth, right. So, sometimes it is also called as, instead of Z buffer, depth buffer, right. So, strictly speaking, it may not be the Z of the word you have, it is actually the depth, right, depending on how you are viewing it, right. So, what we are saying is that, let us say if I have this buffer here for a given pixel located at x and y, the Z buffer value is there as ZBXY, right. And similarly, you would have the information about color of the pixel in the frame buffer, which is CXY, right. Just as the frame buffer contains the color information, you have a Z buffer containing the depth information,
for
right.
each point on the polygon.
For each point on the displayable screen.
Yeah.
So, the window which you have
And for
specified,
and for each of the polygons.
right. So, what is going to happen? Just let me illustrate to you what is happening is that you have a scene like this, let us say, which is containing these polygons, triangles, right. This is the scene I have, and this is what I have is the viewing plane somewhere, right. So, when I say that you maintain the information of depth for each pixel, let us say at x y, now what will happen is I will basically take a polygon, right, plot that, plot means perform the projection and do the plotting of that polygon, and with respect to this pixel I tag the depth or the Z, right. Then I go to the next polygon, I do the plot of it, right, and change the depth if required, whatever that means. We will see what do we mean by if required. That means the depth which was stored, if the current polygon has less depth than that, I change that, I change the value in the buffer, right. So, I update the value of the depth in the buffer and I move on to the other polygon and so on. So, at the end of the day, I have for the pixel xy the depth corresponding to the polygon which needs to be plotted, right, and simultaneously I am updating the frame buffer or the color buffer, right. So, again it is a very simple way of handling Hind surface, right. So, let us see a little more details on it. So, what do we have? First of all, what do? We initialize, let us say, this buffer, which we call it as D buffer, which contains the depth, to some maximum depth. It could be 1, it could be infinity, some maximum depth, right, depending on what range you are looking at. And the corresponding color buffer or the screen buffer, which you may assign to the background color, right. So, if nothing is found to be displayed, it is displayed with the background color, right. So, now what we are doing here for each polygon, so we are basically plotting each polygon. For each polygon and within each polygon for each pixel in polygon's projection, right. So, that means we are doing a scan conversion of the polygon, right. Find depth of z of polygon at x phi corresponding to pixel ij, right, and if this z is less than the stored value of dij, I update the depth buffer and the color buffer or the frame buffer, right. So, that's the algorithm, fairly simple, right. Okay, so computationally what is happening? See, when we are talking about basically scan conversion of the polygon, right. So, we still need to find out the z at each point of the polygon, right. So, what is involved computationally? Let us try to see that. So, if I have this polygon defined as ax plus by plus cz plus d equals to 0, right, at x. So, let us say I am talking about a scan at a given value of x, right. So, at a given value of y, I am looking at various axes, right. That is what I am trying to do, just the way we do scan conversion. So, I compute the value of z for this x, which is this, right, and assume that c is not equal to 0. Fine. Now, what happens to the next point which needs to be drawn? Let us say at x plus delta x, right. I again compute the value of z, which is z1, just by substituting in place of x, x plus delta x, right. So, this is what I get as z1. Now, if you look at the difference between z1 and z, right, the current z and the previous z along the scan line is nothing but this, right. All the other terms are cancelled, the only term which is left is this, right. So, if I look at from the point of view of finding out z1 from z, which was previously computed, so it is just an incremental change to that z, right. So, z1 is z minus a over c times delta x, right, and as we would go pixel by pixel, that means I am going to look at from the next pixel what happens. So, then this delta x is nothing but unity, right. So, it turns out that the new z is nothing but the previous z minus a over c. So, I can actually design an incremental algorithm for computing z. I do not have to explicitly do this every time, right. So, this is along the scan line, right. Is it okay? Okay, so now to take an example, just to elaborate it on further, let's say I take an example where I consider a buffer of the size 8 by 8, right, and I assign the maximum depth of infinity, some big value, to this Z buffer, and correspondingly I have a screen or the display or the frame buffer which I am going to use for color is this, let us say white color, right. So, this is the initialization of my Z buffer algorithm, right. So, now let us say I have this polygon which is to be drawn, right. This is polygon number 1 which is plotted. So, what we notice here is that the Z of all these points is the same 5, right. So, if I just have to look at what happens to the corresponding Z buffer, these values become 5, right. So, here the unity is a unit cell here, okay. So, all I am saying is that these are the updated Z values in the buffer computed from here, okay. Now, I have let us say another polygon which is this, which has got the points as 0, 6, 7, 517 here and 0, 1, 2 here, right. So, here we have different depth at this point, right. So, now I need to do this computation of Z for each of the points of the cell for the buffer. So, this would give me these are as the Z values, right. So, 2, 3, 4, 5, 6, 7 here, 3, 4, 5, 6, 7 here and so on, right. So, clearly you see that this is referring to the depth of this diagonal here, right. So, now when I do the plot of this, I need to update my Z buffer, right. So, when I do that, this is what happens. These are the updated values of Z buffer, right. So, up to this nothing changes and these are the values which are changed, right. So, this is the current Z buffer and accordingly I have this color buffer which contains the information of the color of the respective polygon, right. So, notice here that this value and this value turns out to be same for both, right, and depending on what conditions you put. So, I had basically put the condition strictly less than, only then I update, right. So, this would carry from the previous polygon and therefore, the color of the previous polygon, right. So, this is the way you can perform your Z buffer algorithm. It is fairly simple, right. So, now if you just look at the, just to have a sum up of this, it is a very simple method. If you want to look at from the complexity point of view, the complexity in terms of time, let us say if I have the size of the buffer as n into m, right, and then there are say k polygons in the scene, right. then the order is O n m k, right. So, this is the size of the buffer and k is the number of polygons. And if you just go back and look at the algorithm, there is a for loop for all polygons, right, and then there is for loop for every pixel, right. In terms of space, if I consider, let us say, B as the precision or the, let us say, number of bits I assign for depth, right, then it is simply n m times the this length of the depth, right. This is the storage you require, right. Now, so clearly this is very well supported in the hardware implementation. You are performing operations at each of the cell of the or the pixel of the buffer, and you can do very fast hardware computation, and that is why it is still very popular. Okay. So, now before I ask you the quiz question, do you see the use of Z buffer kind of an algorithm somewhere which we have seen in ray tracing for finding out shadows. So, what is Z buffer doing? Z buffer is basically maintaining depth, right. So, the question which I am posing here is that you need to figure out the shadows, right, in ray tracing, or maybe otherwise also. You may not be using ray tracing to figure out shadows, but ray tracing is one of the ways, right. So, what you do, you basically shoot a ray from the object where the hit point is towards the light source or light sources. Now, the question which is being asked is that are there any similarities in terms of computing the shadow and doing Z buffer?
So, if you maintain the depth from the source, then the closest the point where the depth is minimum, that would be visible, and the one behind would.
So, source, when you say source, is actually light source. What is it?
Yeah.
So, see, conceptually it is exactly the same, because you are replacing the viewer by the light source, and you could still maintain a buffer which is sometimes called as shadow buffer instead of Z buffer, right, for finding out whether a particular point is in shadow or not, right. So, that again requires a pre-processing. What you are trying to do is you may actually put some sort of a grid on the top of the light source, right, which is a buffer, right, and when you shoot rays with respect to each of the cell in that grid, you can figure out whether this cell causes a shadow or not, right. That is what we are trying to address. So, again you can use similar mechanism like a Z buffer to form a shadow buffer, right. Is it fine? Okay. So, now the question which is being asked. So, anyway, we are going to look at some other hidden surface elimination method let's say if I pose it to you as a problem. Now that we have already seen couple of methods of hidden surface elimination, what is the first thing which comes to your mind if you want to resolve this problem of hidden surface elimination? The question is, if somebody asks you, how would you do hidden surface elimination? You know what is it, right? You know the problem definition, right? That what is the first thing which comes to your mind if you are asked to solve this problem? Z buffer. Don't. I don't think so. Now, there is a historical background to it. See, okay, does anybody do painting? At some stage of your studies, you probably did, right? So, what do you do in painting?
So we
It's
create
like you make something, then if you're
Paint
going to
on
make something on top of it,
yeah.
you erase what, or you draw it.
You do on the top of it, right? Right.
But
So,
the problem is that if you're doing it like this, then
So
at least you make it on top of it means that you want to color all over it. So you'll have color mixing, right?
right. So you have to,
Sir, or what we do is like we imagine first what we are going to draw,
and then eliminate the hidden surface in the mind, and then draw only those. But no, I think the natural thing to do is something like if you are doing a, let's say, painting of a scenery where you have to draw a sky or mountains or a moon or a lake or a house, then you sort of go from back to front,
Yes.
right? This is a tendency. So you draw the sky first, or then the mountains, and then the lake, and then and so on. So that is a very natural way of looking at this problem, right? So there is an algorithm which is called as painter's algorithm. Just the way painters thinks, right? So as opposed to floating horizon where we actually went from front to back, a natural thing to do is back to front and keep drawing those things which come front, right? So anyway, we are going to see that next time. So the question which I am going to ask you for the quiz is that, let's see, so we are going to see Z buffer, right? So the A, is it image space or object space, right? That's the first part of the question. B. So we have seen computationally what happens along scan line, right? So along scan line we have an incremental algorithm. What happens across scan line? That means from one scan line to another scan line, right? So this is I was referring to from here to here. Here I am referring to here to here. Does there an incremental algorithm exist? Okay. So you have 5 minutes.
Could you repeat B part?
The B part is that there is this incremental computation right, along the scan line. Right. So, I can compute Z1 in terms of the previous Z computed just by changing incrementally. The question which is asked, can I do this also from one scan line to another scan line? Right. Okay. All right. Thank you.